Okay, wow, so many people here for today. How did the exam go? Okay. Right. No, there's no homework, that's the good news. And the other good news is that since you haven't studied that much since the midterm, we don't have that much to do today. So, I'm gonna review, I'm gonna review the, okay, I talk for you guys, don't care about this. So I'm gonna review the KKT conditions, and then if you have any questions about the midterm, we can go over the questions of the midterm. So no need to worry about the rest. And since you haven't had that much to do, it's just not that much. The exam shouldn't have been that hard. I think it was long, but not hard. Yeah. So how was today's exam? Okay. Okay. So let's have a look at what you did for KKT conditions and the unconstrained problems, and then we'll go over the midterm if you have questions. Otherwise, we'll just finish in half an hour. Today wouldn't be that long. Okay. I try. I always say that, but it never happens. So what we talked about was a notion of convexity. So how did we define convexity in the general sense? Does anybody remember? Okay, let's do something from now on. Those who want to talk, sit on the back rows. Those who want not to talk, sit on the front row, so that I can talk slowly for these guys who want to hear, and those on the back can talk for themselves. I wouldn't mind talking at all, so you can just sit on the back and talk. So from now on, if you're sitting in the front rows, you don't talk, but if you go to the back, you're free to say whatever you want. So, anybody remembers the notion of convexity and concavity in general sense? Yes?
You take 2 points within the set, the line joining those 2 points like.
Okay, good. So if we pick 2 points in a set, let's call them X and Y. Today would be a very easy review, so I don't think you even need to take notes. So we take 2 general points. So the X and Y, and what's the line segment joining them? How do you write it in mathematical form? Exactly. So we define a lambda, which is a number between 0 and 1, and we lambda x plus 1 minus lambda y. Y. So this would be the line segment joining these 2 points. And whenever you forget it should be above or below, you draw this, 2-dimensional thing. And okay, first of all, just a quick review before, this is something. So this is convex or concave? Concave. And this is convex. So if you forgot, concave has a cave, but convex doesn't have a cave. So if you forgot which one is which one, concave has a cave inside it. Now, so if the line segment, the value of function if the line segment is above the value of function at that point, it's a convex function. So we know that if this point is x and this point is y, this is the line segment which is joining them. And we know that the value of the function at this point, so value of function at this point, which is this point, so it would be our function f, value of it at this point is here. It is below the line segment. So this is less than equal to lambda f of x plus 1 minus lambda f of y. And just to remind you fast how we got this inequality, it's not that hard. So we have 2 points here. We have a function here and this. So this is x and f of x. This is y and f of y. Okay? So the line segment joining them would be y minus f of y equals f of y minus f of x divided by x minus y. Well, y, this is not good. I'm using the same thing. So let's call this x0, y0. X minus x. Okay, this is not really a good notation. I used a very, very bad notation. Let's call it x1, x2. That is a very confusing notation. F of x1, f of x2. So the line joining them would be this line. If you remember it from the first recitation, we just reviewed this whole thing. Okay, so this would be an equation of the line which joins these two. You can rewrite it and show that it would turn out to be the same thing that we have there. And then we are saying that if you pick a point here between these two, which is lambda x1 plus 1 minus lambda x2, when lambda is a number between 0 and 1, so basically any point in this line. So we are saying that if we pick any point here, the value of the function should be below the value of the line. If this holds, we say it's a convex function. And if it's the other way around, it means that the value of the function is above the line. We say that it's a concave function. And so this is this point in between. The value of function at this point should be less than the value of less than the value of this line at this point, which is this guy. Using this equation of the line and rewriting it, you can easily verify that being above the function means this, and being below the function means just changing the sign. So this would be convex and concave, and you can always delete this and call it what? What's the difference between these two cases? A strictly concave or a strictly convex or without that. Because, for example, in this case, a line satisfies this. A line is both convex and concave, but a line is not a strictly convex or a strictly concave. So this was some short review. And then you talked a little bit about convex functions and their properties, which I'm not going to go over them. Just the thing that you want to remember, if our function is twice differentiable, being a convex function means that the derivative, if it's a one variable function, it means that the second derivative is positive or negative? Positive. And if it's a multivariable function, it means that the Hessian is semi-positive definite. Good. Well, positive semi-definite, sorry. I don't know, you can use both ways. Then you define something which we called it a convex program. So what was a convex program? That's something that I need to write it somewhere that we keep it all the way here. So is it a minimization or maximization? What's a convex program?
Minimization.
Okay, minimization of a minimization of f of x if this is a convex function, or maximization of a concave function. If you forgot, think of in two dimensions. This is concave. Obviously, it has a maximum. The minimum would go to infinity, minus infinity. So it's either maximization of a concave function or minimization of a convex function. And now the constraints. The greater than equal to constraints. This should be what kind of functions? This should be concave. G of x equal to b. This should be linear. This should be linear. And g of x less than equal to L. This should be convex. Yes. B. Why did I say L? B. So this is okay. So if we have a mathematical program which fits into these conditions, it means that it's either minimization of a convex function, I dropped an error. This is not something new. You have it in your lecture notes. Or if it's a maximization of a concave function, which, you can think of it like this. This totally makes sense. If you have a concave function, you're always talking about maximizing it. Minimizing it, just think of it unconstrained. It would go to infinity, minus infinity. And then for the constraints, you can, find some notation for it, some feeling of it. They all make sense. So, and if the greater than equal constraints are concave, the equal constraints are linear, and the less than equal constraints are convex, then we call this a convex program. Why? Because we will see later on that this is a really nice program. We can solve it. By nice, I mean we can solve it in good cases. And remember, the sign constraints greater than equal to 0, they're all linear. So they are concave. So you don't need to worry about them if you have them. Now, then you define something called separable problem, which, well, for the time being, we really don't need to worry about it. Then we define something called a quadratic program. So a quadratic program is a special case of a convex program. We will have a quadratic objective function. Okay, so if it's in one-dimensional, it would be something like this. If it's more than one dimension, we would write it like this. Okay, so there is the constant term is not important. You can always just delete it. So there's a linear term and there's a quadratic term. So if you have a function like this and you have linear constraints, so you forget about these and forget about these. So this is a very special case now. It's a quadratic function. It's not every function. And it only has linear constraints. Then this one we would call it a quadratic program. And these ones we can solve, which is good. But there is an example of it here which, well, we don't need to worry about it. We'll talk about it later on. Okay. Now, the next step was how to solve these programs. Up to now, whatever we saw were LPs, linear programs, So the constraints are still linear, but the function was also linear. It means that this term was not there. And for those, we have billions, well, not billions. We have a lot of algorithms that solve that. So we are sure that you give, it to do it simplex, do some other method, you find the solution. You just, go from one point to one extreme point to one extreme point. But when it comes to quadratic programs, obviously that method wouldn't work because we are not looking at a linear function over we are not looking at a linear function anymore. So we have to come up with an algorithm to solve it. So there are two ways. Well, so we have to approach it in we have to look at two things. First, we have to find some conditions, some necessary and sufficient conditions that the optimal solution would satisfy, and then give a method, give an algorithm to find it. So we will try to find those two conditions that do this thing. In fact, we'll find them for a more general case for convex programs, but they are easily applied in this case, and you would see that if you apply those conditions for this, you can solve them straightforward. And then we would also be looking at local minimums most of the time, not global minimum. Although a lot of times we like to find a global minimum, but it might not be that easy. But in this case, it would be. It's possible in a lot of cases. But in general, finding a global minimum or maximum is not that easy. You have to look at a lot of places. So we most of the time work with the notion of local minimum or maximum, and then find some conditions that if a point is a local minimum, it is also a global minimum. So we look at things like this. So first we just develop a theory that if a point is a local minimum, it should satisfy these constraints, these conditions. So go through these algorithms, search, find the local minimum, and then we say that, okay, if the program fits into these conditions, this local minimum is also a global minimum. Done. So that would be what we will be looking at. Now, okay, we will look at a problem like this. minimize f of x given that a set of equality constraints and a set of inequality constraints. We should put all of them in this case. Less than bi. Really doesn't matter. You can flip the sign with multiplying it by minus. And we give names to them. So we are trying to find conditions such that a point like x star is the local minimum. Let's see what we can do. First of all, we have to look at the conditions. We look at the constraints which are binding. So these guys are always binding. You're always on them. But these guys, some of them are not binding. Some of them would be, just strictly less than. So for our algorithm, we really don't care about them for the time being. So we define a new set. We call it I, which in your lecture notes is defined, has a typo. So if you want to fix it in your lecture notes later on. So this is how it's defined in your lecture notes. Which I is the set of active constraints, but in fact it should be this. So what are the active constraints? These are always active, and some of these guys are also active. So we look at all the union, all the I's, and pick those which are satisfied at equality. Obviously there would be all of these and some of these. So all of these and some of these, which we call them set I, is the set of points, is the set of constraints that are active at point x star. So now we are saying that we know that x star is the local minimum, and we define the set which is the set of the constraints which are active at that point. Now we want to try to characterize x star. What condition does it satisfy? The only thing that we know for the time being is that it's a local minimum. Now, the first thing is we linearize this guy. Basically, we approximate it by its Taylor expansion, which we did in the first, I think, few lectures. So this point would be written as, I hope this should be clear by now for everybody. So if it doesn't make sense, let me know. I think this is the only step in this whole algorithm which might be a little bit confusing. Okay. Now, does this thing make sense to you or no? What's it saying? Somebody tells me that. What does this thing mean? Sorry?
First order Taylor series.
Would you talk louder? I can't hear you.
First order Taylor series.
Yes, exactly. So this is first order Taylor series expansion. But what does it mean? Good. So what we are doing is, as you said, we are assuming that, what we did always before. So this is f. We are assuming it with we are approximating it with a linear function. Assume that you are standing here. You're saying instead of looking at this curve, I'm going to look at this line. This is in one dimension. This is multidimensional. So the gradient would give you all the directions. You multiply it by d vector. And alpha is a point that is just a number that you can move how much you want in this direction. Does it make sense now? This is obviously what kind of multiplication? Huh? Inner product or dot product. This is a vector. This is a vector. I don't know if you remember or not, once we were talking that I was telling you that if you have a function and you want to find the rate of change in direction d, how do you find it? We said it's the dot product of the gradient and that direction.
Shortest point down the mountain.
Yeah, exactly, something like that. So this was what I was telling you before, that if you have a function and you want to, at one point, you want to go to one direction, just one direction, and you want to, so it's like this. Let me draw a picture. So assume that our function is this guy, this surface. So you're standing at this point, and this is the value of function at this. Now, you want to see that if you go in this direction, what would be the rate of change there? How did you find it? We said that we look at the gradient at this point, and we find its dot product with the vector that we move, and we find the rate of change. Of course, this should be a vector of size 1. But in this case, because of this alpha, it doesn't matter really. So you are changing, you are going in direction d, you have this gradient, so the dot product would give you the rate of change. And alpha will tell you how much you want to go in that direction. So basically, this guy is saying, instead of looking at this surface, which we don't know what it is, look at a straight, just look at the linear case instead of looking at the surface, which is not linear. Or in a one-dimensional thing, instead of looking at the curve, look at the line. Okay? Does it make sense? Yes or no? There's either yes or no answer.
Yes.
Ah, good. So we are saying that standing at this point, we look at the linear case. Now, we are saying that this guy was the minimum, and we know that it's the minimum. So, well, this is the next step, but I'm going to go. So before doing that, before doing that, we also look at the linear approximation of the constraints. Same thing. Okay? So we look at the linear approximation of these two guys too. So it would be g of x star plus alpha d transpose gradient of g. I'm using the same notation that you have in your lecture notes, but it really doesn't matter if it's the d transpose multiplied by gradient of g or the other way around. It's the same thing, because we know that dot product doesn't matter the order. So that's why here this guy comes after, this guy comes here. There's no reason behind it. It's just that you have it in the same way in your lecture notes. So these should all be equal to bi, and these guys should be less than equal to bi. If I'm not mistaken, do I have it correctly? Yeah. Okay. Now we can simplify some stuff a little, which is good. We know that x star is a minimum and is the feasible point. Okay? So for x star itself, gi of x star, if I is in E, equals to what? Hello? B? Okay, YB? Yeah, because it's a feasible point itself. So it self-satisfies this condition. So we know that gi of x star equals to bi. So this guy and this guy cancel out for I in E. So we will have for I in E, alpha d transpose gi of x star is equal to 0. This is the first thing that we will have. The same thing here. We will know that gi is less than bi. So because of this, we will know that bi minus gi of x star is greater than or equal to 0. So if you write it down there, the same thing would happen, that you will get for I in I. Now I'm going to explain this a little. Alpha d transpose gi of x star is less than or equal to 0. So basically what we did, for those which were satisfied at equality, we just cancelled out these guys and we got this thing. And for those which are, and for the others which are satisfied at equality but do not come from these, we just write down the same condition and we get this. So nothing really fancy. We just cancel out using the fact that x star is a feasible point itself. Now we can also drop this alpha. It's not really important, because even if you want to take this to be a negative thing, just take the negative in D and make alpha positive. It's not really important. So we write this thing only for positive alphas. So basically we are saying if you want to go in this direction, you pick D. If you want to go in this direction, you pick minus D. So if you can always play with your direction, you can always pick a positive alpha. So you also drop alpha and you get these conditions. So these conditions would be what we need. The first step that we are going to do this thing. So our linearized problem, the problem that we instead of looking at this problem, minimize f of x with these conditions, we look at the problem with these conditions. Minimize, okay, I will leave the objective function for a second. Gradient of gi x transpose d is less than or equal to 0 for I in I, and gradient of gi x transpose d equals to 0 for I in A. And minimize gradient of f x transpose d. So let's see what we did. So we are trying to find a d. No, forget this. Forget this. Now, here also, instead of minimizing f of x, we'll be minimizing the linear approximation of it. And what I'm saying that this is a fixed number, f of x 0, a star. So just forget it. It's a value. It's a number. And we drop alpha. We just need this part. So instead of doing that problem, we are going to do this problem. Minimize gradient of f of x with these conditions. Yeah.
What do we do with constraints which are not binding?
Okay. The constraints which are not binding, it doesn't matter because you can make this approximation for them. Okay. And they are, if you pick alpha a very small number, this would still be non-binding. So it will be something like this. Let me write it down for you. So, for example, it would turn out to be like this. Assume gix star equals 3, which was less than or equal to 5. Some number like this. When you make it linear, it would be 3 plus alpha gradient of f of x star d less than or equal to 5. Okay? Since this number will not be infinity, it will be a big number. Assume it's a huge number, 10 to the power of 5. You can pick a small alpha enough. You just make alpha a very small number. This would still hold at less than equal. So just a second. So all those which are strictly less than equal, you don't need to worry about them. You just pick a small alpha and they would be still non-active. But those which are active, you need this constraint. Yes?
Shouldn't there be a gradient next to this too? The D's transpose.
Oh, sorry. I just, yeah, they're the same thing. I just forgot to write them there. Yeah, the gradient should be there. So that was a good question, in fact. So what I said was, we had this problem. We wanted to find, we know that x star is the local minimum. We want to find some conditions that this guy is satisfying. Instead of looking at the problem which we don't know how to deal with, we look at the linear counterpart which we know how to deal with. So, but why this linear thing would be valid to look at? Because we look at linearization of this guy. We see that g of x star is equal to this. So this part should be equal to 0 so that it's feasible. And also this case, less than equal, should be less than equal to 0 with the same method. Just put this thing there. And for those which are not satisfied at equality, we pick a small alpha. They are still not active. So instead of looking at that problem, and here this is a fixed number, alpha is positive. Instead of minimizing this whole thing, we will just minimize this part. So we say instead of doing those things, minimize this part with these conditions. So this will be a problem that we will look at this. Now, if x star is the local optimum, the gradient at the local optimum is what? Is the local minimum is 0. So it's a stationary point. Assuming it's a station. So we are assuming that the function is well behaving, everything is nice. So the minimum would occur in a stationary point. So this gradient would be 0. So the objective function would be 0. So if you find the feasible point, okay, which the objective, which the minimum here would be 0, then you're fine. Now, we are saying that this guy, with this if x star is minimum, the optimum here, the minimum, would equal to 0. Okay? So we look at its dual now. So I'm going to erase this part now because we don't need to worry about them. The only thing that you should keep in your mind is that instead of looking at this non-linear problem which you didn't know how to deal with some just logical reasoning, we ended up looking at its gradients, which if it's a quadratic function, the gradient would be 1 degree less, it would be linear. But if that's not quadratic, this wouldn't be linear. Okay? But still, it's just 1 degree less than that. So instead of looking at that problem, we are going to look at this problem. Then we said that if x star is minimum, the gradient has to be 0. So the minimum of this function would be 0. So we look at its dual now. Okay. Writing its dual can be a little bit... Okay, so we would be maximizing 0 transpose V. Okay, where did this 0 come from? I'm writing the dual of that problem. Where did this 0 come from? So, the right-hand side vector is only 0. That's why the objective function here is 0. Subject to sigma I in E, gradient of Gi x star Vi plus sigma I in I, gradient of Gi x star Vi with Ui, doesn't matter, equals gradient of f of x star. Yes? Okay. Yes. Do you hear my voice? Okay. Sorry, guys. So, now, with Vi less than equal to 0 and Vi free. This is for I in I, and this is for I in E. Let's see how did I write this down. So basically, I just assigned a vector V to this part. And, so the objective function would be the right-hand side transpose V, and the constraint would be each of these multiplied by V equal to equal to the coefficients here. And it's equality because all the D is free. So since it's free, it's equality. So we know that that problem has a 0 optimal solution. So its dual is also feasible and has a 0 optimal solution. Now, there is a small theorem here which the whole thing that we are building, hinges on that, and it's called KKT conditions, basically, these guys, and we can write them in a second. Now, the theorem that we are dealing with says this is really important. If x0 is local minimum, so this is 1, and 2, gradient of Gi of x star for I in I are linearly independent, then we will have that Vi satisfied okay, I'm going to use what everything here. A. Okay, I have to. I'm being a little bit lazy here, just using my old stuff. I in E plus sigma I in L, gradient of x star Vi equals gradient of x star Vi vi greater than equal to 0 for I in G, vi free for I in E, and vi less than equal to 0 for I in F. And C, which we call them complementary cycling conditions, is vi gi of x star minus vi equals for R. Okay. Now, this after all this stuff that we wrote down, we wrote down the problem, we looked at this gradient version of it, and we looked at the dual of the gradient version. Then there were these guys who came up with this theorem that said that if x star is a local minimum, and if these gradients of the active constraints are linearly independent, both of them are important. If either of them is violated, this doesn't hold. So if it's a local minimum, but these are not linearly independent, this theorem doesn't hold. So if it's a local minimum, and if these gradients are linearly independent, then those VI's which solve the dual problem would satisfy these constraints. First of all, this summation. So this is just summation over the greater than equal, less than equal, and equality constraints. The gradients multiplied by the VI's. Equal would be the gradient of the objective function, or the gradient of the objective function at the optimal point. Basically, it's saying that you can synthesize it by using the gradients of the G. And then there's the sign constraints and all these VI's. If you are worried about greater than equal, just change them to less than equal and change the sign here. So basically, you can write this thing only with 2 sigmas. That's what I did before. It's not really important. And the third thing is that these VI's would satisfy this condition, which we will call it, what are the G's? Okay, G are the greater than equal constraints. These are equal constraints, these are the less than equal constraints. So let's call these G, L, and G. But you can always change G and L.
This problem we don't have this.
Yeah, this is a little bit more general than this, yeah. But don't worry about G. If you are really worried about G, just erase them, multiply all of them by negative, they will be all in L type. So you really don't need to worry. Oh, they are all in primal. So I'm just saying that. So basically, what we came up with is this. Let's look at the big picture of what's happening here and get a feeling about this. See? Okay, I'm going to talk about it. Then let's get a feeling about this condition. It's too abstract now. So we had a primal problem. I wish I hadn't erased this dual, but it's okay. So we had a primal problem. We know we can assume we can solve it, and it has the optimal solution. And also we can write a dual for this, and write down the dual problem and solve it and find the optimal of the dual group. Now these conditions are in a way connecting these two set of solutions. Basically, what we know is that for each set of the optimal primal points, the solution, there is a dual solution too. So it's saying that if you pick optimal solutions of the dual, and if you pick the optimal solutions of the primal, then together they will satisfy these constraints. That's the beauty of it. So it's saying that instead of going and solving either of these two problems, if you can solve these, just try to find a set of variables. These are some equations. Find some numbers that would satisfy this. These, some of them positive, some of them free, some of them negative, that when you put them there, these constraints are satisfied. Then it's saying that instead of going and solving those two problems, solve these and they would give you the same solution. The solution would be the optimal solution. Yes?
X0 is x12?
X0, do I have X0?
Up there.
Yeah.
So the gradient is 0.
Is 0.
Objective function. In the first equation.
X0.
Yeah.
The gradient is 0, right?
The gradient would be 0. I think that's right. Just make sure. Yeah. That is 0. I think that is 0. You can write that. Just give me a second. I think that's 0. Yeah.
VIs are vectors?
Yeah, VIs are not vectors. No.
They are not vectors?
They're numbers.
They're not
Oh.
they're linearly independent then if it's equal to 0.
No. These are. Let me just see what I say. Okay, so these are which are at a strict equality with the linearly independent, not all of them. Okay. Now, let's see. So this guy has a specific name which we call it. I'm going to tell you what these guys mean. Okay. Basically, what these guys mean in big picture. Forget all this. There are 3 sets of constraints that if you satisfy, you can find the optimal solution of these 2 guys. You have to find a set of numbers, points, that are dual feasible, are primal feasible, and also satisfy this weird condition, which we will talk about right now. So the idea is you have minimize f of x. I'm going to write it down in LP, but it's not really important. I think I've written the correct one, have I? I think so. It's not really important. I might have made it this time. So what I'm saying is, if I find a set of x's, which are the variables which are the solution to these, and if I find a set of p's which are the variables that are solution to these, and x's are feasible here and p's are feasible here, and they satisfy this thing which I call the complementary slackness condition, meaning that if a constraint is not binding, if this constraint is not binding, g of x star is strictly less than bi, then the dual variable for that constraint should be equal to 0. So if the dual variable is 0, then so if the constraint is not binding, the dual variable would be 0. If the dual variable is not 0, the constraint would be binding. It will be equal. So if I find a set of is binding, then this is not binding. So if this is binding, then this is 0. If this is not binding, then this guy has to be 0. If vi is strictly greater than 0, then this means that gi of x star is equal to 0. So if we can find these set of numbers, then you have find the optimal solution. And if you look at these two, they have a good feeling with the meaning of those shadow prices that you were talking about. We are saying that if a constant is not binding, it means that if it's satisfied at a strict inequality, then the dual variable is 0. It means that the value of raising the right-hand side will be nothing. You already have excess of it. You don't need to raise it even more. The other way around is saying that if it's satisfied at equality, it means that you have reached the limit of capacity for that constraint. So raising it would have some value. Not necessarily this can greater than or equal to 0. But you can be sure that if raising it has some value, it has been satisfied at equality. Otherwise, you would have raised it. Yes.
Isn't C already satisfied by A and B though? Like even if you didn't have the C condition in there.
You mean that if you have A and B, then C holds?
Yeah. Because isn't it true? Like it's like an LP. Like that's always going to hold.
This is not necessarily linear.
Well, that's I know, but isn't it follow the same? Doesn't it follow the same type of principle? Like if in an LP, I'm just using this like sort of as an analog or whatever.
Okay.
Like if you have an LP, if you know that the primal is feasible and the dual is feasible, that has to hold, like, no matter what.
Does it?
Because you're at the optimal solution.
Yeah, because you have a...
Does that not hold for
no, not
linear program?
Not necessarily. I don't have it on top of my mind.
Okay.
Yeah. So, basically, what we have here, this is a little bit more general than the setting of the LP case. So this is a linear case, and these guys, we had these shadow price things. It makes sense. This is more general than that. We are not talking about linear constraints anymore. So if these two conditions that we have up there hold, then we know that the VIs, those set of numbers, will satisfy these constraints. Now, still these VIs would have the interpretation of the shadow price, if you raise it by right-hand side by a certain amount. Now, these things are called KKT conditions, and basically there were these three guys who came up with them, Karush, Khan, and Tucker, that said that if you have a good set and convex program, blah blah blah. If you have a local minimum, it would satisfy these conditions, and then they came up with when are these necessary and sufficient conditions for this point to be local minimum or global minimum, and it was a master thesis. So, it's a very simple problem, but it's just that these guys looked at it the first time. Now we are trying to look at, okay, we have this theorem, these conditions. Let's summarize what we have taught and see what these conditions mean. So let's see if these guys hold under what conditions this would be a local or optimal minimum, or a global minimum. Now, so all these, what we want to bear in mind is this part. If you have x star and v, so there's a set of x's and a set of v's that satisfy the KKT conditions. Sorry, these are the necessary conditions. So necessary. So if your x star and v are the minimum, they would satisfy the KKT condition. So if the minimum is x star and v are the counterparts for it, they would satisfy these conditions A, B, C. And they will also satisfy this extra condition. If you define a matrix here. So if x star is a local minimum, it will satisfy B transpose M of x star. C is greater than phi 1. So if our point is a minimum point, it will satisfy these three constraints. And if it's a local minimum, it will also, for all the feasible directions that you can go, this will be a positive value. Yes?
Do all this hold for maximizing the concave function?
Yeah, you can do the same thing. Yeah, whatever we do for, instead of maximizing the concave function, just minimize its negative, and then everything will follow. That's why we just look at one. So this would be the necessary condition, meaning that if this is a local minimum, this would hold. And what we are maybe more interested in is the sufficient conditions. So if you find a set of x0 and v that satisfy these guys, and also D transpose M of x star D is strictly greater than 0, then obviously D is not equal to 0, then this would give you that x star is a local. So if you are doing a convex program and it satisfies the KKT condition, then, sorry, if you have a set of points that satisfy the KKT condition, then this guy holds, then x star is a local minimum.
Do you say that if x star is a local minimum, then they satisfy the KKT condition?
Yes. Yeah. So the first one is saying that, remember, we are not talking about convex programs, we are talking in general. So you will see that in convex programs, these gradients, this would be 0 because all the constraints are linear, and this would be just a number because it's a second degree thing. The second derivative would be a number. It would be a matrix of the numbers, and it would be, if we talk about it, that matrix is semi-positive definitely. So this is general case. In a general case, if you have a set of points that satisfy the KKT condition, if you have the minimum, which is the x star, it should satisfy the KKT condition, and if it's a local minimum, it should also satisfy this condition. And if you find a set of points which you don't know if they are minimum or not, but you know that they satisfy the KKT condition, and they also satisfy this constraint, then you can be sure that you have found the local minimum.
Just,
Yes.
there's some, you said that this is general case.
This is a general case, yeah.
But, this is, you took a convex objective function.
Yeah, I didn't prove it in a general case.
Okay.
I just, so you can just draw a line here. So we are not really proving the whole thing here. It's just to give you a feeling that in some cases where it might come from. Now, so everybody knows the difference between sufficient and necessary condition, yes? Just to make sure. Yes or no?
Yes.
Yes. Okay. So somebody tells me what's the difference between the Are you sure you know? Let's see. Let me give you an aspect. Okay, I assume you know. It's not really that important. So necessary condition means that if, in our case, it means that what should the local minimum satisfy, which is this, and sufficient condition says that if a point satisfies, these conditions, it would be definitely a local minimum. And it's obviously, look, so this is just a sufficient condition. So sometimes you might have a minimum point that does not satisfy this. Okay? It might just satisfy something else and it still be a minimum. But it should definitely satisfy this. Now, and the last case, yeah, this one is very good. Just a small thing to bear in mind that if you have only equality constraints and nothing else, so this is a little bit more general because they were not necessarily only equality constraints. So if you only have equality constraint problem, you just need x star and b to be KKT to be a KKT point, basically satisfying A, B, C. I deleted A, and also you need x star to be the unconstrained minimum of f of x star minus sigma vi gix star minus. Okay, so if you remember from your calculus, this is what you just got Lagrangian. So if you only have equality constraints, you don't have any other constraints, you multiply the equality constraints by a vi and add it to the f of x and find the minimum of it, just taking derivative setting equal to 0, find the unconstrained minimum, and then that would be the minimum of your whole problem. Now, just to bear in mind, what are the conditions for this whole thing to hold? X star should be a local minimum, and this and is very important. All the constraints which are satisfied at equality, they should be linearly independent. If your constraints are not linearly independent, none of these guys hold. Okay, so that's also a loophole in the whole thing. So if it's a local minimum, and if they are linearly independent, then these will be necessary conditions for a local minimum. These will be sufficient conditions for a local minimum. And this will be necessary and sufficient conditions only for a problem with equality constraints. Okay? Now we have a set of tools that we can apply to our problems and try to solve them. I think there's time, this part is there, yeah. Let's look at this problem that is solved in your lecture notes. And then we will be, that's a good news for you. So, let's see what we had in your problem. It was minimize x1, x2, plus x2, x3, plus x3, x1, subject to x1 plus x2 plus x3 equals to 0. One thing that you would know about convex programs, so what we define there as a convex program, minimizing a convex function over convex set, was you will see that the KKT conditions are both necessary and sufficient. That's something nice about it. So you just need to check the KKT conditions and everything will go. But I'm not sure if you have, I think you will talk about it in the next lecture, but you will see that Nice thing about those quadratic programs or all those complex programs are that KKT conditions are both necessary and sufficient. So you don't really need to check this one. Why? Because this M matrix for a quadratic, for example, it would turn out to be a Hessian if you are talking about the complex program, because these would turn out to be 0. So if the Hessian, but F is a convex function, though the Hessian would be semi-positive definite, so if it's semi-positive definite, a lot of things. Now, let's look at, so for the time being, we assume we don't know this stuff, and we just go through the example by the way it's going. So, gradient of f of x should be, so we write it like this. So it's just writing this value. So we are synthesizing the gradient by the gradient of the G matrix. This is the first A condition. So this would give you, so the gradient of f would be derivative with respect to x1, x2, derivative with respect to x3, and derivative with respect to x3, which would be x1. So x2, x3, x1. Oh, sorry. X2 plus x3, x3 plus x1, and x1 plus x1. So this would be the gradient of f of x. So this should be equal to v. Now, gradient of g, since it's linear, would be 1, 1, 1, 1. So this would give you xi equals v divided by 2. This is what you get from the first condition, A. So we know that the minimum should satisfy that the set of this guy should satisfy the first. So this is KKT condition A. Now, the second one would be the sign. So this would be A. The second one, B, would be the sign constraints for B. But x's are all free. So all of them are in the case of I is in E, which will give you Vi is free. So there will be no constraints on sign of V. And the last one is, it should, and also it should be it should be also a primal feasible point. So we know that this guy should hold. We combine this with this constraint. So we know that this is primal feasible, and we put this here. So we will have 3v divided by 2 equals to 1. So v would equal to 3v divided by 2 would equal to 3. So v would equal to 2. So combining this with this. So we know that our problem is dual feasible because Vi is free. We know that it's primal feasible because we satisfy this one. And the only thing which remains is to check the second order condition, which is this M of x. So as I said, in our case, G are all linear, so the second gradient would all vanish. They would all be 0. We just need to worry about the Hessian matrix. So the Hessian matrix would turn out to be 0, 1, 1, 1, 0, 1, 0, 1, 1. Okay, which this is what? Is it a semi what? Okay, we don't know about that, so we just multiply it by D and D transpose. If you don't know if it's a semi-positive definite or not, you don't know to take the eigenvalues or anything. Just remember, a matrix is a semi-positive, positive semi-definite matrix if it satisfies this. So we pick a vector D, D1, D2, D3, and multiply it by this matrix. This is nothing more than this. So this is our M matrix. Multiplying it would give you D transpose MD would equal to minus D1 plus D2 plus D3, all of them to the power of 2, strictly less than 0, when D is not equal to 0. So we had this problem. we found a set of points that satisfy the KKT conditions. How did we find them? They satisfied the dual feasibility, they satisfied the primal feasibility, and they also satisfy this gradient condition. So we have x1 equals to 1, x2 equals to 1, x3 equals to 1, and v equals to 2. So they satisfy the KKT conditions. And we also found out that the D transpose MD is strictly positive for any D non-equal to 0. So basically we are satisfying the sufficient condition. And you can also check that they are linearly independent. Why? Because there's only one. There's only one G here, which is obviously linearly independent. So this point is the local minimum of our problem. This was a very easy case that writing down the KKT condition was easy to solve, and they turned out to be really nice problems. Now, but a lot of times solving these wouldn't be that easy. Here, solving them turned out to be just solving one linear problem, something that you could, you had such a nice thing, you only had one V. But a lot of times, if this is a function which is not quadratic, if this is a function which is not linear, then your M matrix wouldn't be something nice that you can easily argue that. Just a second. Your M matrix wouldn't be a nice matrix. Your equation wouldn't be something nice to solve. So you will see that in case of a quadratic problem, we can solve it. Yes, what was the question?
Yeah, over there you said it's positive semi-definite.
Well, you really don't need it to be for positive semi-definite because you need it to be for all D primal feasible. But in this case, it is.
So what are you checking with that?
Oh, well, I didn't know if it is or not.
Right.
So remember, what was the definition of a matrix being the positive semi-definite? No, that was not the definition. What is the definition? Yeah. So we said a matrix A is positive semi-definite if this thing holds, and if it is positive definite if this thing holds. Okay? And then we came up with some conditions that if this holds, it's still the same thing if the eigenvalues are positive or blah blah. So in this case, it was just a matrix of numbers. So I easily just wrote this thing down and verified this thing. So I basically verified the definition. I just multiplied it by a vector D, and this is another D. So I just verified that this would turn out to be something which is always there. Yes?
Normally to have local minimum, we should have it positive, no?
Minimum is a concave function. The second derivative is negative. So the
Minima is convex, right?
This is convex. Sorry. It should be negative or positive. Let me just see what it is. So maybe I was just talking about. Sorry. Sorry. That was a maximization problem, not a minimization problem. And let's see why. Okay, it's obviously a maximization. Well, not obviously, but I think you can find the minimum should be unbounded. I think in this one. Take 2 option to minimum infinity and this one to positive, and then this thing negative infinity, and positive infinity. Yeah, I think it would be unbounded if you want to minimize it. It's a maximization.
But why though? Aren't all three of those, if you do that little separate each term thing, they're all three convex, right? So isn't three convex functions the convex function of itself? Shouldn't the minimization problem be like...
Is it x1 multiplied by x2 convex?
If you have like x, y, or...
They're all three variables. It really depends on which quadrant you're talking about.
Well, because if you have like... If you have x, y equals c, right, then 1x is going to be equal to 1 over, or c over y, and that's the convex function.
This is a two-dimensional function.
Yeah, but I'm
it's not a We are here maximizing a function. Just write this time. That would be a concave function. It's not concave. Why is it a concave function? Because the Hn is negative. Just check it. It will be a concave. It's not a concave. I don't know. Well, it's a 4-dimensional. I don't know how to draw it.
Right.
But try to draw this one at least. I don't think. I'm not sure if the 3-dimensional one would be convex or concave. So it's not easy to say that they are convex or concave. You should just write down the definition and see if they turn out to be convex or concave. Yes.
So that's what your definition over there is reversed. That's what I was asking. The definition you wrote on the right side of the board.
Okay, convex.
It should be reversed now.
Well, I didn't know if this function is convex or concave. I checked it. I saw it's there.
It should be less than 0, right?
It's less than 0.
Yeah, wait, I know.
Oh, this is for local minimums.
Yeah.
This is for maximum.
For local maximum.
Yeah, it's the other way around.
Exactly.
Yeah.
That's why I was asking.
No. So the question somebody asked if we can everything holds for maximum. I said multiply it by negative and then do it for minimum. So if you just multiply everything by negative, hold it for minimum, or just flip the sign and don't multiply by negative. You know what I mean? So you just said change this to maximum, this is less than equal, or multiply the function itself by negative and don't change this. It's just whichever combination. Basically, it would have turned out to be this. And instead of doing that, I would have done this. And then the whole thing would have held, and then there would have been a negative here, and this would have been positive, and then this would have held as positive. So I was just saying that, you either do it with minimum or maximum, depending on your function. Now, the last step is, the next page is not that much hard. So then, we talked about Lagrangian method. Which Lagrangian method, if you remember it from long ago, it was for problems which only had equality constraints. So if you have only equality constraints, it means that your VI's are free. You just write down this and check if it is check the Lagrangian and see if it holds or not. Just to get a good feeling about it and see why it is the same thing. Look at this. It's not really important. It's not something that you would look at. So I'm just saying that the Lagrangian method is nothing more than the KKT condition only for equality constraints. So
Lagrangian could be, we can have
yeah, but we're talking about Lagrangian with equality constraints. Because if you have inequality constraint, then you basically need the KKT condition to just double check everything else too. You have the problem on signs and everything. The nice thing about Lagrangian for equality constraint is that you wouldn't care what your v's turn out to be. Whatever they are, you are fine, everything is nice. If you have less than equal, then the sign of v is important. Remember, we all know how to solve an unconstrained problem. By unconstrained, I mean no constraint on any sign or anything. Just take, since we are talking in differentiable case, we just take derivatives on those. Then, there is a small thing that is proved at the end, which you can just read it yourself, it's not very important, which will prove that if our program is a convex program, this local minimum turns out to be a global minimum, which is nice. So if you're talking about the convex program, then by doing these things, you find the local minimum, and then you're suddenly guaranteed that this was a global minimum. But if you're not talking about convex program, sorry, we don't know anything about it.
So, is 111 the local minimum here?
Yeah.
And we're saying it's a global minimum?
Yeah.
But
Maximum, that's minimum.
So that should be max then?
Yeah, we changed it to max. Yeah, I changed this thing to max. Maximize of x1, x2, that's x. That's the maximum. That's the minimum, maximum. So if you're talking about the convex program, suddenly everything becomes nice. That local minimum becomes maximum, global minimum. That local maximum becomes global maximum. Both of them hold. And which is really nice. But remember, this is really important. If this thing doesn't hold, then none of these things hold. Okay? So if you don't have linearly independent constraints there, then none of these things hold. Then basically you don't know how to solve it. Okay, that's the problem. And at the end, there was this example that you couldn't solve it easily. There was, I think it was the Markovitch problem. The bounded short sets problem. That was the example. of programs which were convex, but even you couldn't solve these equations. They just turned out to be hard problems to solve. And then you have to go through these numeric methods of searching for the optimal solution. The idea is you pick a point, you look at the direction, which is a good direction, you go a little in that direction. A little means a step which you have to determine. So there will be problems of picking a first point, then picking the direction, then picking how much you want to move in that direction, and then you go there and check some conditions. If they are satisfied, you say I'm optimal. Otherwise, you again choose a new direction and you go in that direction and choose it. Basically, this is what we even did in simplex, if you remember. We picked a point, we checked the direction, then we said this is the step. We came here, then we checked some conditions. Are we optimal? No. So we again look at this direction, we go, we find the step size, we go here, we check, are we optimal? Yes, we stop. But there we were guaranteed that it ends in a nice, really fast way, but here we are not guaranteed. So we will talk about later on, I think, next lecture, or maybe the lecture after that, about the methods of finding them. Have a good day.